So we're going to see today, again, design considerations and construction considerations related to industrial slabs. As I did in the previous lectures, there is, one of the things, as a practicing in the construction industry, typically there is a lot, like very simplified guidelines for the engineers to use, which kind of led all people or the whole community to know what to do. And that's what make the footpath look same everywhere, or particularly for one council. The curbs, the curb in the roads, if you walk in a suburb or like governed by one of the councils, they almost look really same, because the construction company is going to follow a standard for that council, and that's why they have to look same concrete qualities, same specifications, same dimensions, same. So basically there are very handy documents, and I'm highlighting here the one which is very well used locally, which Cement and Concrete Association is kind of a private organization which is hired by government institutions to stipulate and put down specifications and guidelines. So they kind of look at the standards available and then take the main points and simplify them and put them in a document like this one. So this is the document I was highlighting as green. It's this one. You have it, you have access to it as a reading material, and it's really, you can find it in the net anyway. It's very useful to, if you're reading or managing a project like this, it will just tell you maybe the main key requirements to consider when you're constructing such floor material. Also, like at some stage they talk about the processes to do some of the steps. For example, the curing. You know what curing is? Can I ask people what curing is? What do you mean curing? C-U-R-I-N-G, curing. Any idea what, you know what I'm saying? Cure concrete. Just unmute and give us a quick answer. We talked about it as well in week 1, but that was for suspended slabs. Now we have industrial slabs. Curing process, it is, when you pour a concrete, sometimes the concrete, for the concrete, when it change its status from wet concrete to hard concrete, it's going through chemical process, and we need to make sure the water content will not evaporate quickly. So curing means we need either to spray it, make sure the water still in the mix by either spraying water or covering the. There are three main ways. One is spraying the mix. You don't spray it in day 1. You're going to spray it in the next for 3 days, and there are standards, and this document simplify them to you. So they tell you if you have this type of concrete with this grade, and that's what you're trying to achieve, then you need to cure it for 3 days, right? So you need to come next day, spray it, and day 2 same, day 3 same. Alternatively, you can cover it with wet sheets. Alternatively, you can just use admixtures. Admixtures, they are chemicals that you can put to the concrete, and that will help to retain the water in the concrete until the mix gently take place. So that's just this kind of steps. They are available within this document. If you think, always it's good to look at the table of contents. There is construction considerations. So chapter 2 really talks about all these things. Maybe chapter 1, it's not strongly, it's good to know about. We will talk about things. Chapter 1 is to do for the design engineers. Chapter 1, that was chapter 1, design engineers. Chapter 2 and 3, I think it's useful for construction engineers or strongly connected to structural engineers. Now, how this is going to be used and assessed, it's again, we have used some of the notes we have here in our lectures. So again, as per what I agreed with you, if there are tables or charts I have used in a workshop to practice things, so you may be doing same thing in a final exam, but I won't be digging for things here to ask you about. You can stay and keep limited to what we're talking about over the lecture notes. So whatever we talked about in the lecture notes should be enough, because we kind of took most of the main points there. We will come to. So it's really good document. It's good to know about. Keep it in your library. And I'm sure most of the, especially young engineers, they start working in the construction for many developments, which definitely in the end they will have industrial slabs. And it's good to know about it. So yeah, that's it. So I was just trying to mention to you, today we will be talking about some design considerations, just so you know about, and then we're going to cover construction methods and considerations. And this green document, it's kind of used in developing these lecture notes, and it's good for your library as well. Right, so as one of you have answered, just when I ask what you think the main difference or the key difference between normal residential slabs and industrial slabs, and the answer was heavy loadings. That's totally right. So you can see here there are three main types of loads that can be imposed and applied on industrial slabs. First of all, uniform distributed loads. Okay. Now, the loads, which we assume they are like a blanket, like a pressure. That's what we mean here. The load is spread. The load is spread over an area. Okay, that's a uniform load, which the engineers will assume they are kind of maybe planks or any materials that are distributed over an area. Just to compare and see, as I said, your residential loads can be 1.5. Commercial can go to 5 kPa. That's the residential. That's just the normal loads. The people, you know, in the shopping or like a warehouse, we consider the life loads there from the users and the people who walk around. They can get up to 5 kPa, which is 500 kilograms per meter square. Factories and warehouses, no, it's pushed too high because they can store heavy materials there as well. So it's between a very, very heavy 20 to 100 kPa, which is 20, you can imagine is 20, it's 2,000 kilograms per meter square. And this is just a lot of 10,000 kilograms per meter square. So that's the first type of loading, which is UDL, and PL, point load. Yeah, point load, definitely it's highly possible in residential. When we design a car park, yeah, we consider point load, but it's going to be as much as, I think, 5 kilonewton as a maximum, because we consider what's going to happen from one wheel of a car onto that driveway. And I think 5 or even less than 5 kilonewton as a maximum point load. Here you can see we engineers consider between 30 to 120 kilonewtons. Now, why you want to know these numbers? You are not a designer. In case you have to install something, if you want to install, maybe you decided to pour your slab before putting your portal frames. You want it because some builders like to actually pour the slab because the site is very wet and it is a rainy season. They don't want to keep the dirt, the soil, over the construction time because it slows them down. If it's muddy, they can't move the vehicles, they can't move and operate fast. So what they do sometimes, they pour the slab from day one, and then you have to know from the documents what's the maximum point load. You don't want to bring a crane or a forklift which is more than the acceptable range, because you will crack that slab and build it again. So that's why you would need to have an idea what point loads a particular slab was designed for. So that's what it's not only about the final use, it's also during construction. You need to pay attention to such limits, because as I said, in many cases, the slab can be poured even before putting the roof and the portal frames, because it's better for that particular situation. So yeah, loading can be from 30 to 120. Obviously, the slab will be more expensive when you go to this side, more steel, more concrete. So if it's not required, you don't need to go that far, maybe 50, maybe 40. So yeah, point load can come from construction point loads or in-service construction, in-service loads like the racks, which we're going to see pictures like these are, I would say these are uniform load. This is uniform load. Yeah, we said that here. They are uniform loads that you can imagine, and these are the ones which can go between, as we said here, between 20 to 100 kPa pressure, depends again on the density of the materials and how high we go up. Okay, and you can say, why I need to worry about this as a builder? Maybe you're going to be putting construction material there, so make sure it's within a limit. These are the point loads. You know, these are the storage racks. They will end up, you know, we will end up having a point load on the slab. So as I said, point load can happen in service when the slab is in service. And also you may have a forklift moving here or any other crane to bring things up and down. I think most of you have been in IKEA. IKEA, it's a very nice example to really think about. IKEA, I think it's close to Bandura. It shows you this kind of environment. And most of what we studied is kind of covered here so far, like from week 2 to week 4. So we were talking about point loads. As I said, it's not only about during construction, it's also about in-service life, drop-down legs on semi-trailers. That's also during construction. Yeah, you may need to lift up your roof rafter or lift up a set of purlins. Purlins is not delivered piece by piece to the contractor sitting on top of the roof. They are delivered as a grouped set of members. Okay, so that was type 2. We're talking here about the type of loads that the slab suffers from. We have 2 types of static loads, as we said, uniform and point, and here we have dynamic loads as well. Dynamic loads as well. Dynamic loads basically comes from the forklift or any other moving. Usually, just to let you know, dynamic load is higher than static because it's got inertia inside it. As a very simple way to look at it, dynamic load is simply higher by a factor. So engineers go through many steps to find out that factor. Like maybe if we said the static load is 20 kPa, let's talk about point load. If we said a static load is 30 point load, if you want to worry about a dynamic then, because a forklift at 1 point load weighs 30 kilonewton, for example. But then you're worried about dynamic load because that forklift may be moving and suddenly stopping. Okay, when it stops, it's going to be pushing the ground harder because there's a gravity and there's an inertia, acceleration. So engineers will be calculating factors to amplify this. So it may go to, that factor may be 1.5, so we end up 45. Instead of 30, 45. So, and again, that's why you can see we start talking about tons here. It's really heavy. Tons is heavier than kilogram. This is 8,000 to 28,000 kilograms. So And that's basically a summary of the 3 types. They can happen together. Why not? Yeah. So that's why you would have your industrial slab much more thicker, more expensive. Not only that, just to let you know, and we're going to talk about this more. So just to go through those pictures, that's another example for a point load. As we said, this is the drop down legs from the truck because they can't keep it on the wheels when they unload. They would put it just to distribute the load as well. Hi. What else? Forklifts. Yeah, we said that as well. We can have heavy point loads on the front wheels. That's why you would see typically they make the front wheels bigger, because from engineering, whenever the contact area is bigger, the stress will be less. Whenever the contact area is bigger, the final stress will be less. Whenever we make the contact area bigger, you're reducing the stress on the slab. So basically, to stabilize, it's not our job to look at how this is working, but we're talking about the slabs. So as a construction engineer, basically, if you're using these in your construction, just send email to the contractors and tell them don't go above this many of kilonewtons with your point load on the wheel, on one wheel. Yeah, and then if they did it, they're gonna fix it for you. Right? Or eventually you always need to make sure, because you don't need to spend time to fixing as well. It's not really helpful. What else? Yeah, just talking more about forklifts and the wheels. So we're talking here about the loads. You won't see these type of loads on the residential. Yeah, we see forklifts, but they don't carry a lot of loads. They just carry lightweight things. Like because I know some of you see some type of those forklifts. Well, they are for cleaning houses or buildings, and they won't be that heavy. But the problem here is with what load they're gonna carry. That's why we get to the 8 kilonewton, 8 ton for a dynamic load, or 28 tons for a dynamic load. But you won't see these type of loads on a residential project. Right. So we talked about loads, and we're done with talking about loads. So that section, try when you read those notes as a preparation for the final exam. I know it's coming in, you still have time. Try to kind of classify and understand which part is talking about what, so you don't really get mixed about what we're talking about. So first we were talking about loads. Now we're going to be talking about the subgrade. Subgrade, it is what's under the slab. And just to let you know, whatever I talk to you about in terms of how expensive are those slabs, etc., there is another big bill in case the soil below the slab is poor quality, is fill, it's kind of rubbish. There's a lot of areas in Melbourne where it's just a fill area. Fill means it's not a clay, it's not a sand, it's not a natural material. That's what I'm trying to say. It's not a natural material. It's just a fill where things have been, like, if they want to create a trend, especially in the Docklands area, or I think Port Melbourne as well. There is a lot of fill where they thrown aesthetic soil material there, and they kept doing this ages ago. And whenever you build something there, the soil report will tell you there is about 2 meters or so of fill. So definitely you're gonna need piles. You're gonna need piles, and that's additional cost. Which again, if you don't understand what the drawings are saying, you may miss that. And if you sign a contract to build something and you missed such issue, that will be costing. Sometimes even a good advice for the developer who's developing this property or trying to build the warehouse and sell it or rent it. It's good advice from you as the engineer. to tell them, go and get soil reports. Okay, even before you buy maybe the land. It's not only in Docklands. There's a lot of areas which is basically fill for more than 2 meters. I think yeah, there's a lot of suburbs which got kind of fill. Maybe it was an easement. No easement ages ago. They did a lot of excavations to put the main pipes. That's the easement, and the areas surrounding such facilities are typically fill. And so it's very advisable for people when they buy a land next to an easement or even an existing house. Like you see a lot of houses, old houses, where developers who got the money, they want to demolish it and build a new units. One of the key things is to make sure there is no main easement, because if there is an easement with about 1.5 meter diameter pipe, imagine that most of that land is filled. And then what does that mean to the developer? Is it's going to be very costly footing system. Why? Because, you know, if this is your slab, this is the slab, concrete slab. Ideally, you would have the slab sitting on a subgrade, yeah, like acceptable, or like a natural ground, compacted natural ground, and then happy days. You're just going to design this to carry all the industrial loads. But in case you have fill, it will have not acceptable. It will not reach 20 or 50 kPa bearing capacity, which is very weak. In this case, what we do, we have to use band beams, like a suspended slab, and use piles that needs to go 3 meters or 5 meters into the ground, which is a lot of money. So that's really my key summary here, is kind of why understanding subgrade is really important for the development. It is to do basically with the, yeah, because the load gonna go from the object or whatever equipment you are mobile, you know, moving above it, and then goes through the slab. The slab's job here is just to take the load safely from the top surface to the bottom. That's all it does. But again, the big problem is how the ground is working. So that's why careful site investigation needs to be looked at. If you're looking into such project, make sure the soil report was adequate, giving the right information, and the engineering document was using the correct documents to make sure the subgrade strength is adequate. And there is one of the, again, here we're talking about design considerations, and one of the like the simple steps to kind of find the capacity of the soil of the subgrade. Subgrade means the material under the slab, is by looking to charts. One of the key parameters is modulus of subgrade reaction. So this one, basically, there is a test that the soil engineers will do. You know, there are soil engineers and there are structural engineers. Soil engineers go and investigate the soil. In residential projects, they do very small, thin report, which does not need all these type of tests. Okay, so when you do a slab for industrial development, you will need to do more proper parameters, and these parameters like California bearing ratio. It is a test which it will be conducted on site, and then the soil engineer will give you a figure for that type of soil. Then from that figure, the engineers can work out the modulus subgrade reaction. It just tells the engineers how many kPa the soil can take, which is the key answer. And that's kind of a very simple way to look at how it does work, and it will be good for the construction even engineers to know about it. So again, if this was our industrial slab, let's say it's 150 thick. This is the concrete industrial slab, say 150 thick, and I'm trying to write here 150. right? And there is a point load. Say there is a point load. How does it work? The point load will be distributed by 45 degrees over the concrete, right? When there is a load from the post, the load will be distributed by 45 degrees. That's just the rule of load distribution, 45 degrees. Then it's going to get to the soil. So what we do, we divide that point load, say it's 10 kilonewton over this area, which comes from the 45 angle of repose distribution. Then after you found that stress, you just make sure where it's going to sit here. That's all you want to. So if the soil, again, let's do it slowly. If the soil engineer will say that California, they call it CBR. They will tell you what's the CPR value. If the CPR value is, let's say, 15, then we go to 15, come here, let's say we have about what? Midway, say 65 kPa per millimeter. Okay, 65 millimeters. You just need now, the standards will tell you how many millimeters is acceptable for the soil to be settled at, settled like displaced. So now what we're saying here, the soil engineer is telling us if you're gonna put 65 kPa on that soil, it will be displaced what 1 millimeter, which is really acceptable. It's not a problem at all. Some standards will tell you don't go more than 5 millimeters. So here you're definitely okay with this. That's what I say. My example of having what did I say? 10 kilonewtons. It's very small number. All right. So we can do some examples later, but basically you just need to understand how to read this chart, and that will be kind of what we're going to be talking about. So basically, CBR will be given by the CBR is typically given by the soil engineer. And if he give you a figure, you will be able to know what's the maximum kPa pressure a soil can take. That will give you 1 millimeter. And the standards on the other side will tell you how many millimeters you are allowed to settle a soil. That's how simple it is. Okay. Any question? So while we're here, let's do a quick example. Let's assume the pressure you have from a post onto the slab is actually 500 kPa, right? So the pressure, let me call it sigma. Let me use a pen. Let me tell you the pressure on the soil. I don't want you to calculate the angle of repose. The pressure on the soil S is equal to 500 kPa, right? And the soil engineer is telling you the CBR, which is the California bearing ratio. Let's say it is 20. 20%. So can someone tell me how many millimeters the soil will be settled at? How many millimeters the soil will be settled at? Yeah, can you tell us how you did it, Ivan? Thank you, but tell us how you did it.
Hello, sir. I just divided, 20% in the graph is
Excellent.
equivalent to 70.
That's
So
right.
I just divided 500 kPa by 70.
Well done. That's it. Yeah, we see how easy it is. Yeah, and then as which is 7 mil, the soil, the subgrade will be settled, kind of compressed, pushed down, and then that number will be, so let's say you have a portal frame like this, like what you are now experts in building portal frames, yeah? So then this 70 mil, so let's say this column here is pushing by, I know it's a lot, it's a very big number, by the way, 500 kPa, but I'm just giving you example. So that means the soil here will be settled by what? 7 millimeters. Then it's up to the design engineer to say if this is acceptable or not. Now, where is your role? What's your job here? I know you're not the designer, but you need to make sure these numbers are working together. Yeah, you can't bring a forklift, which is more than this figure, because you may end up settling the slab more than and eventually cracking. Because, you know, after they find the 7 millimeter that you calculated, they will make sure the slab can take it safely. The industrial slab can actually flex it without getting cracked. If the slab cannot flex and take it, then it's a problem. So that's how it's really working. All right, so that was just talking about, so there are more information about it, but the key thing we practiced together, and it's a question like how to use this graph, and you know how to use it. Now we have just more information about the subgrade as well. You just need to know it is, as I said to you, it depends how you're going to be distributing the load. So for example, it is the construction engineer decision when they got a material delivered on site. You don't need to put all the material at one spot. It's going to be too heavy. You can actually distribute them over a bigger slab, and that's part of your planning. How you want to really get things done. I think what the note here, the statement is saying to you, you don't need to have a rock always. Sometimes the slab is the soil is very strong ground, so that will be happy days for you. Like it's easy ground, it's good ground. I know some people don't like always to have rock because you have a rock site, it's going to be too expensive to put your piles, the piles footings for the portal frames. It's going to be difficult to excavate and knock down the rock. Yeah, I think I've talked about these kind of points for you during construction. Uniform support may be lost, and again, if you have expansive soil or fine graded soil, it's going to be difficult to. So sometimes what's going to happen if you have very soft soil, and it's something like the fill I was talking about. It's very difficult to control. Things can be actually moving, and that's another difficulty in construction. If you have a very, very sandy site, you have for you need to carefully study the situation of the soil, because it's not only about the design and safety of the building, it's during construction. It may cost you a lot to build a site with expansive or finely graded grade soil. It means that it's kind of very sandy. You can't even excavate a hole, right? So if you want to excavate a hole, the soil will keep coming back to the hole, and that's cost, and you need a lot of propping and a lot of. So it depends. I mean, there are cases. So you just need to. The point from what we're talking about here is you need to know about the soil condition or the subgrade condition, because it will let you budget it correctly, time it correctly, You don't need to get surprises. And if it was written in the soil report, so you should have been knowing about it when you price a job. Okay, so you can give the correct timing needed and the correct budget needed to get it done. Yeah, these are like a good notes for you to know. Site conditions that can lead to distortion of floor slabs. Expansive. So expansive soil means it's kind of very flexible, very soft soil that can expand, and like very, very sandy or very fill material. Now sand, yeah, it can take bearing, but you have to make sure it's stabilized. When you excavate in a sand, it's harder. If you have a deep footing to do or a pile, when you excavate it, there may be special material to use. We're going to talk about piling in the coming weeks. So it will end up kind of impacting the condition of your slabs. Also, the moisture content got an issues, but usually the geotech engineer will give you guidelines. And the document I was referring to will give you also processes what to do. In terms of, there are, like sometimes if you have a site, if you're a developer bought a site and there is a lot of trees there, trees, trees, they suck the water from their footings. And if you decided to take the trees away, you're going to change the moisture conditions. So what sometimes they do is, if you have this, you have to dry the ground. There is a process geotech engineers know where construction engineers will be drying. Like for the first meter, there's a process where they need to dry and compact the ground to let its moisture content getting stabilized. Alternatively, what's advisable as well is they remove the trees maybe 6 months before the construction time. So they let the ground settle by itself. There is a lot of techniques to do this, but you just need to know the main. We won't ask you in the subjects what to do, but I just want you to know how the slab can be impacted by, especially those industrial slab, if they build them for storage. As I said to you, those storages also are built for retailers like Woolworth or Coles. They build these kind of facilities in the middle of the farm, and there are a lot of trees and vegetations around. So when they take away the vegetations, the soil, the moisture content will be very dynamic. It will not be stable. And you need to think about ways to get it stabilized. As I said, you either wait for several months, or you can dehydrate the soil. And yeah, there are sometimes different, the soil is not, sometimes you see in the topography of the soil kind of properties change. You have sites where you got 0.5 meter of fill, which is just deposited material. Then another part's going to be basalt, then another part may be clay, then you go back to, so again, the soil report will tell you all these things. It's not your job to make a design, but you need to know about it because you're going to build it. That's it. So don't think, yeah, the engineer will do all what they have to do to design a proper slab. The soil engineer will do whatever they do to excavate in the soil and make tests, but you need to know how much it's going to cost you and the limitation of construction. So that's basically what you need to do. You don't need to do the numbers, just need to know about the problems that can face you and ending up disturbing your construction process. So the document I showed you at the start, it's really give you an idea as a construction engineer to know what do we mean with coarse, because the soil reports, usually they're going to use these terminologies. So this is kind of give you idea about the subgrade. That's why I said the document that I shared with you first, T48 from Cement and Concrete Association, they kind of simplify things. We don't go too technical and math and all these kind of things. It's good. This one tells you how critical is the subgrade that I was talking about. Is it good? Is it medium? All the numbers and details and designs should be done correctly by the engineers, and they are responsible. as a builder or construction engineer, you need to make sure it's built in line with specifications, because engineers or geotech engineers will tell you the condition need to be confirmed on site. Like if they said put the footing on a clay, you have to put it on a clay. If they said put the slab on a dehydrated subgrade, you have to allow for some money to dehydrate it, and you call another company to do it for you. So that's really why you need to know what we're showing you here. So this document basically is, it's good to just read through. There is a finer grade soils and there is a coarse kind of a bigger grade soils. These are the kind, that's what they refer usually the soil reports. They write this in the reports. So if you are within this type, you will know this is acceptable and good, and it should build sense for you how things are going. Okay. Highly organic soil, it is an issue, and again, it's poor, and the engineer should have been telling you what to do. The soil engineer or the structural engineer should have been telling you what to do. Sometimes there are like arborist reports, which is kind of tree scientists who look into the trees and how they keep, you know, sucking the water from the ground and keeping it around the trees. If you have decent unmature trees, you may ask to involve such engineers. So yeah, things can be very simple, no issues, but some other things can be over complicated. Any questions? Okay, so that was really about, I think these are the notes related to subgrade. Read through them, understand the tables, pay attention to the chart, and that's basically what we want you to know so far. Now, reinforcement. Obviously, you will definitely know those industrial slabs, even the residential slabs, they got reinforcement inside them. All right, they do have reinforcement still. Someone will say, why we just don't pour the concrete, the gray concrete on the ground and make it look nice? Can someone tell me quickly why? Why we have reinforcement inside the concrete? I know for suspended, you know, when we talked about week 1, suspended concrete slabs, we said because the slab is flexing, you know, it's going to flex like the dotted lines I'm showing you. Usually we're gonna have the bottom side under tension, the yellow side under tension, and we need the steel there to take the tension. But can I ask you why we would think about, like, if we have even residential slabs, why are we gonna put steel inside them? Any idea? So this is your slab. It's going to be built on a good subground or subgrade. So why would you put steel? It's such a section. Why are we going to be putting steel? They also will have some sort of steel inside them. Yeah, basically, when you pour the concrete as a wet material, as you know, over few days, it needs time to get to the hard status. And during that time, it's gonna what? Shrink. During that time, it's gonna shrink. Shrink means it's gonna reduce its size. Now, what's gonna happen is the slab will start cracking. Who can stop the cracks? The steel. The steel will stop cracking. So when it shrinks and try to move, it won't shrink by 1 meter. Talking here about millimeter, like fraction of a millimeters. So when it's shrinking, there are gonna be some cracks developed. Like it's gonna try to move. It's gonna cracks developed, and to stop those cracks, we're gonna put steel to lock in and prevent those cracks. All right. So yes, there is reinforcement in any type of slab on the ground, and especially as well the industrial slabs. Now, industrial slabs, if they are, again, they are heavy loaded, and they're gonna flex as well. and they will need either not for industrial slab, we're not worried about shrinkage only. We are also worried about the flexure, because I will show you very useful diagram here. Yeah, you remember we showed you something which was opposite, upside down, for the portal frame, or when you studied engineering. So what we used to see usually, we used to see a beam, and you've got the supports under, and the beam will carry loads. Yeah, so it's from the top, and then you're going to have your bending moment diagram, which looks like this. With industrial slabs, things will be upside down, because this pressure, it's actually the reaction from the soil, which we said it's good condition. It's a good subgrade. So when you put load, they're going to be pressure from the soil going up. And these point loads are the legs of the racks or the storage units or the forklift, whatever it is. And that's it. So it's just the same thing. It's just upside down. Okay, so what I'm trying to say, the steel we use in industrial slab, it's not only for shrinkage, it is also for taking a flexure action, like what we have in normal beams. So that was really my point. Now, I think this section here, what we're trying to highlight to you is industrial slabs. They will typically have joints, which we will talk about. Sometimes industrial slabs are jointed, and what we need to do there is to actually allow for the reinforcement to be kind of continued. The slab, the steel cannot stop and start. So typically reinforcement to cross particular joints, unless if it's a movement joint. We will be talking about joints next. Sometimes we have, or let me clarify this to you now, what this statement is talking about. What's going to happen with if we have steel in the floor and there is a joint, there is a kind of a movement joint, we're gonna then now need to allow for an opening. So let me just show you. If this is a concrete slab and you poured it up to this point and you stop because the day is finished, or maybe it starts raining, right? So this is industrial slab and you poured it, then you stopped the pour. Then tomorrow you want to come back and continue the pour. In this case, you have to continue your steel. You have to make sure the steel is sticking out, and then your new steel gonna come and lap with it. You have to lap between the previous and in your steel. That's if it was a construction joint. However, if it was another type of joint, which you actually want the slab to move, to maybe because it's a permanent movement joint, then we should not allow for the steel to continue, because we want the slabs to independently walk or like move away from each other. And you see that in some of the like movement joints, we call them in the shopping. Let me just see if I can show you an example what I'm talking about. See if yeah, like these are just some sketches. So these are kind of movement joints. Now when you walk, let me see if there is better images. Yeah. Okay, you see something, that's what you see when you walk in a shopping center. You're gonna see just a nice plate in the top. This is actually a movement joint. And what we're trying to say here, the reinforcement should stop. There is no reinforcement. So this concrete slab stopped here. Then you're gonna continue after 10 millimeters or 15 up to the engineer, which is something like this as well. So we call this as a movement joint, and the main steel should stop. The main steel should stop. We cannot allow it to go from one side. We call this as a movement control joints. We have more slides to talk about movement joints, which I will come back to. Okay, so just while we are on this section, just understand there are different types of joints, but mainly they are divided to movement joints, which the engineer wanted, because you can't pour a slab for 100 meters in one go. because there is heat and all these kind of things, it's gonna crack. So usually the slabs can run for 30 to 40 meters, and you start another one. So what we have to do, you see them when you walk in any shopping center, you're gonna see, because they are very long. You're gonna see these plates, as I said to you, and that means you cannot continue the slabs. You have to stop the pour and start another kind of structure. If it was construction joint, because the day is finished or it started raining, you have to stop the pour. We have to construction joint, and in this case, you can't continue the bars to lap together, right? So we will talk more about joints types in the lecture, and you should know more about this. Here we're talking about reinforcement, and the reinforcement, again, as a key summary for this, it is to do from the engineer. The engineer will tell you the quantity and type of steel you put, which is the mesh steel in the. You can see there was a picture in this document. So whether it's a bar, this is a construction joint, by the way, which I will come back to. We have many pictures talking to us. We can also talk about this during the workshop. But quantity of steel and the number of bars, it's again designed by the engineer, which you don't need to change. You just need to place, and you place it in line with the cover. And there was a project which we will use in our, I think from next week. This is a project, it's a school project. Okay, it is a school project, which I will introduce to you next week. It's part of the retention system, the retaining walls we're talking about. But it's got an industrial slab, kind of a slab. It's not industrial, this is school. But really what I wanted to show you here is this is a plan. This is the plan, that the page which talks about the details of the slab. And here you can see the slab is 120 thick, and you simply just need to go and read about the floor slab, and that's it. You're going to be given all those details from the engineer, whether this is a school project, but again, same thing for your industrial project. So they will tell you what maximum load it take, the concrete strength, the type of steel, top. In industrial slabs, you typically will have top and bottom because of the reason I told you, because of that bending moment diagram. This was just the classrooms where they only need the steel at the top. There is also the waterproof membrane, which have to be there. So it's basically specified here in this document. And also the subgrade, the subgrade needs to be compacted. So usually the subgrade, don't think that it's going to be just cleaned by truck and that's it. Or no, it's going to need to be compacted to specific values, which is done by the contractors usually. All right, so that was just an example of what we mean with. There is another type of reinforcement. So we have steel bars. That's what we're talking about here. But there is another type of reinforcement where they put steel fiber reinforcement. It's kind of, let me just type it. I think the best way is to type it here for you, steel fibers. It's kind of a smaller place. Okay, what they do here, there are some industrial slabs which are sitting on a good quality subgrade, and you don't want to use steel bars. What you can use kind of fibers, which will do the same job as resisting the cracks, the shrinkage cracks. So in summary, what I'm trying to say is in industrial slabs where you have a very good subgrade, does not flex and can take all the load, you just need a slab that transfers the load because it will not flex. So your problem is with shrinkage. These kind of reinforcement, which is kind of steel fibers, it can be mixed with the concrete. And it's expensive, just to let you know. It's not really cheap. So the steel bars are cheaper, but this one gives you much high quality. It controls the cracks very well. And if you need a very smooth, like very minimum cracks, or micro cracks, which you can't see. Definitely some, yeah, you can. Some people, you know, they still use the steel bars and put this in the mix if they need to achieve kind of minimized cracks in their slab. They can use these in their mix. It's going to help a lot, and it will, as it says here, it's going to help resulting in a thinner slab. So it can help to resist all those shrinkage cracks and help to minimize even the steel quantity you need to put. But this is, again, qualities can be discussed during the design stage. And that's where you need to know about it. Maybe it's written in the documents. If you miss it, you're going to be paying for it. Okay. Talking more about slabs, this is another chart here which kind of gives you an idea. It kind of gives you idea about if we don't have steel in the slab, what's the maximum tensile it can take. So this is just telling you the flexural tensile capacity for the concrete itself. And that's where engineers will start thinking about putting steel to make it resist more. Regardless, as I said, there are minimum steel. You can't see a pavement slab with zero steel. This is not possible because there's shrinkage. However, that steel can also be used for flexure because shrinkage will happen only during the process of hardening the concrete. Then as a permanent use, yes, the minimum steel we placed can be used for flexure. Now, sometimes that steel is enough, sometimes not. And there are charts like this, which will tell you what's the maximum it can take and what the maximum the gray concrete can take. And this chart here shows you it's a function. So the maximum tensile capacity the gray concrete can take by its own, it's in function of the concrete strength. Usually we may have 40 MPa. So you just plot it here. So that means you can actually resist 5 MPa tensile. If 5 MPa, if the engineer basically found that 5 MPa, it's going to crack, it's going to be reached, or you're going to have more stresses, then you need to start putting steel. So this is, again, I would say this is a design. We just want you to know what the engineers are thinking about. So basically there are stresses, whether from shrinkage, which you have no choice, you have to control it with steel, or from loads like this. Yeah, didn't I say we have this bending moment? Bending moment will result in stresses, like flexure stresses. You got a bending, a flexure, it will result in a flexure stresses. Those stresses, if they go above 5 MPa, then we need to know that the concrete cannot take it. So that's where, I mean, the engineers uses such chart. This chart, again, it has nothing to do with the steel. It's just telling you what the gray concrete can take by its own in terms of MPa tensile flexure. MPa tensile flexure. The engineers will go through calculations for statics. They're gonna find the flexure stresses from loads. If they go above 5 MPa, for example, like this, then they just have to put steel to deal with it. But this is just to let you know how the process is going to go. All right. Another point is what the slabs can suffer from is fatigue. Fatigue really comes from dynamic loads because those type of slabs are under forklift, truck, under impact. So usually again, this is really, now I know you can ask, as a construction engineer, you're going to follow drawings, specifications, and what correct. But when we're talking about fatigue, it means the engineer going to be using special type of steel that will look after the flexibility of the concrete, which is typically, you remember when we talked about the type of bars, we have normal ductility, like if you reset N20, N12, sorry, the 12 is not nice, N12 at 200. What does this mean? This means your bars will be placed every 200 millimeters, and it's classified as N, which means normal ductility. you cannot go in a project and use a different ductility level, like maybe L type, low ductility. There is another type, L12. L12 means low ductility. Remember, if you have if on site, it's cheaper. Low ductility is cheaper, and maybe what can happen? Maybe you're gonna find these type of steel available from a different project, and you may say, "Let me use it here. It's just same size. Happy days." No, because in industrial buildings, you have to know it's different than residential. In residential, we may use low ductility, right? Because we may have some bikes for the kids or like lightweight cars driving above it. That's all. So low ductility is not is acceptable, but don't think that maybe you finished a project where you had extra steel available in your warehouse. You can't use it in industrial because industrial they can be stressed. Not with all the stresses and loads we talked about here. It also can be under dynamic fatigue load. To control and resist such load is we need to have a steel with adequate ductility because the steel will allow for the concrete flexibility and everything should work correctly from there. Okay, another key thing you need to think about as a design. We're still here kind of talking about design and we are under the concrete properties. So far, we talked about reinforcement in one page. And here we started talking about concrete. That's why I was highlighting to you this chart has nothing to do with steel. This chart, it is to do with the concrete. The gray concrete, it's very good in taking compression, okay? It's weak in taking tension. However, it's got some capacity to take tension. And as I said to you, if that concrete take 40 MPa, a lot of compression, it can take only 5. And sometimes the tension stops under 5, sometimes goes above 5. If it's under 5, then you don't need additional steel to resist flexure. You just need it for shrinkage. If it's above 5, then they're going to be, the steel need to be increased. Okay, so that's basically the knowledge you would need to know as a construction engineer. But all the calculations and numbers will really come from the engineers. But you just need to know what you're doing. You need to know how, you need to know a lot of details in the car to know how to drive it. Okay, like you need to know the big road rules. You need to know what the signs means to drive in the road. You cannot just jump in the car and drive. Okay, so we got more kind of things for you to know about in terms of concrete properties. And one of the key things is durability. You have to build things where it's going to last longer. It's going to have the same quality. What controls durability is you make sure the quality of the concrete is on top and the strength that was used is on top. And yes, for you, you just need to read it correctly from the drawings and apply it. Okay. And again, the document I'm sharing with you gives the engineers good idea about what can be used. So if we're talking about heavy traffic and some mild chemical attack, which is applicable for warehouses, then light engineering works. That's the typical application. So it's, as I said, that document, the T48 document, it's very handy for you to use. And it will end up telling you what's typically the strength. Someone will say, don't the engineer will do this? Yes, the engineer will say this in their drawings. Okay. But you can't discuss things with the engineers if they have used this. In the end of the day, the construction engineers, they are looking to the project and they're going to be the first contact point to be responsible about building a project, not. So the client won't go to the engineers. They will come to you and say why this failed. You then can go to the engineer and argue with him. But the engineer maybe is telling you, is telling you to confirm this. Maybe the engineer didn't know. He will come back and tell you, I did not know this is going to be used for mild chemical attack. The engineers maybe have done that project 5 years ago, and he didn't know really what's going to be used for, right? Maybe during those 5 years, a decision was made to change the service of that slab from medium to heavy, and he may not know, the engineer who did it. So those numbers, yes, you should make, sense them. And as I said, there are simplified documents for the construction engineer to use. Now, you're going to ask me, for us as a students in this subject, do I need to memorize those tables? No. No, you don't need to. If there's a question about them, but what the question going to be, just tell me what type of strength you're going to be using, and you're going to be given a document like this. In your exam paper, you may be given 5 pages, which is just materials you're going to be using. Again, talking about exam going to be closed book. You can take nothing to the exam. And it's going to be, you just need to study where you understand what each sheet is talking about. That's all. Well, I won't tell me what type of floor, or I won't give you this and let you guess this number. No. I may give you the whole table, and by looking to the table, tell me which one to choose. So as simple as this. But people who really don't look at those pages until the final exam, they mess very well. They don't know which even page to use, because as I said, you may be given 5 or 7 sheets, like tables, the span tables we used last week about the purlins and girts. Yeah. So you may have another page talking. So some students may not know which page to use, and they really struggle in the final exam. But don't expect I'm asking you to memorize those types, or they will be given to you. You just need to know how to use, because in the real world, you're gonna have access to it. So no point. And if someone's gonna tell me why we don't do the exam open book, you're gonna need your travel bag. I don't want people to come with a big bag to the exam. You're going to waste a lot of time to search for the answers. And again, it does not. Just need to read the sheets and ask us if you have any questions, and things will be, and just learn. So we are 9:20 now. Let me finish a part, and then we may have short break. Let me just continue up to here, and then I have short break. We may finish some of the slides during the workshop as well. So this sheet, yeah, it's another one which is very friendly to know. Can someone tell me what this sheet can be used for? Someone just unmute or just tell me. As a practicing construction engineer, where you think you're going to be used, and what does it tell you? It's just self-explanatory. You don't need a lecture to tell you. My point is just to tell you what you need to think about as a construction engineer, what document to use. But some of those charts are very friendly and easy to use. So can someone tell me what is this chart is telling us? Mm-hmm. Is it difficult? Yeah, basically it's the relationship between the front axle load of your of a forklift and the thickness of the slab. All right, so these charts are actually developed by design engineers, and these guidelines are typically used, which tells you the tonnage a front axle will take. So remember, each wheel will take half. Each wheel will take half. And then there is internal loading and edge loading. When we say internal edge, is at the edge of the slab. So if you have, if I go back to those pictures I showed you, and so yeah, you see this is the control joint. This is the forklift. This is the front wheel axle. So both of them, yeah, both of them we're finding Muslim. Now, usually if the engineer want to check the edge line, because usually the edge line get heavily affected by the loads than if we are worried about non-edge. So whatever really, it doesn't matter if we're saying 1 meter or 5 or 6 or 10, because someone will ask me, where is the internal? It's not the edge. So anything away from the edge. So when we check, now someone will say, this is quite practical point here. Someone will say, as a builder, what should I worry about? The edge? Let me ask you this question. I just want you to talk with me, guys. So what I just want to put a question here. But before I put a question, let me finish explaining to you the chart. So the chart basically, the horizontal axis talking about the front axle maximum load it can take. And the vertical axis will help the engineers to confirm the thicknesses, right? There are more equations to use, but this is a guideline, right? So this is just the thickness. But I just want you to tell me, and remember there are some specifications like the tire pressure going to be this much kPa, etc., which is a standard. So all good here, right? What I want to ask you here and discuss with you is, as a construction engineer, where are you going to be worried about internal loading or edge loading? What does it matter for you? And while you think about this, just know you have different lines here, which again help you to decide or also consider the CBR, which we talked about, the California bearing ratio. Now, my question to you, I just want you to just engage with me and tell me when you would think about, or what does it matter for you? Which one you're going to look at? If in which scenario or situation? Just give me any thoughts you have. Do you want a break and think about it? All right, just take a break up to 9:35. Let's take a break. Can someone just say anything over just to make sure the communication is working? Can someone just say hello or something?
Yes, hello.
Thank you. All right, so let's take a break to 9:35 and just tell me, when do you think you will be worried about the edge landing? What does it matter for you as a construction engineer, whether it's edge or internal? Now, I said to you, edge is a close to the edge of the slab or a control joint. Now, I don't know where's in this picture, where's the edge of the slab, but there is sometimes control joints like this, which we will talk about. And what does it matter for the construction engineer? Why or which figure you're going to go with? All right, think about it, and we will meet at we will meet at 9:35. Hello, students. The answer? Any answer there? So what I'm saying, if your slab thickness, say you have built a slab already, you've already built a slab, and the slab was, say, only 150 thick. The concrete slab was only 150 millimeters thick, right? Which is at this level. Okay, and your CBR was 5%. Okay. Can you use the forklift and where? Can you use the forklift and where? All right, if not answering now, definitely going to be answered. So the way you should think about it, it is in such case, you have to make sure that the forklift will not come near the edge loading, because you can see 150 does not cover any situation for edge loading. So you need to make sure that the contractors, when they're using such forklift, they have to be away from the edge loading. That's one thing. And also the maximum capacity they can get up to, if we said CB R5, then simply that's the maximum forklift tons they can have at the front axis, which is say about midway or less than midway. And that's say 7 or 6.5. So you're just going to be limited by this much of tonnage. Okay, so that's how you can use such chart. And what does it mean for you? It's not only for design engineers, it's for construction engineers. Maybe during construction, you want to have some materials delivered or craned by a forklift or any other lifting equipment. Just always make sure the loads will be limited by the thickness of the slab. As you can see here, 150, first thing you need to worry about, stay away from the edges. Edges means the edge of the slab or control joints. And the other thing is these charts will tell you what's the maximum loads the forklift can have on the front axis. So basically, these kind of arrangement we can use the charts for. So we're talking here about thickness design, which it's definitely controlled by the post loads that we can have, whether from the storage shelves or racks or whatever we have there, or a forklift or any point loads from a truck, the drop down loads. It will be controlling the maximum post load, the load contact area, the spacing between the posts. So all that gonna come into effect. And again, these things are considered by the designers from day one, which is not the builder. Why you need to know about them? If things is changed, you may need to consult the engineers again. So it's not about you make a decision and change the setup. If maybe, as I said, the design engineer designed those drawings 3 years ago, and for whatever reason, the architect ask you, like they can ask you to change the layout of the storage units, and the placement for the racks, you have to always make sure it will be working for the slab by contacting the engineer again, whatever it really needs to happen. Because as I said to you, these are just the point loads, the legs from the, so these squares, they represent the legs from the storage shelves, like these ones here, like these ones. So basically those squares I was showing you, they are the legs from the racks or the shelves you have in a warehouse. And if we look here, they're spacing the size of the legs, their spacing, they will help the engineers to work out the thickness of the slab. As I said, basically, it will go back to what we do for a suspended slab. It's just going to be suspended, although it's poured on the concrete slab, but it is eventually suspended in a reversed mode. All right, so distributed loads and objective of their design. Usually, as we said, during construction, you will have the decision in distributing the loads. If the point loads will increase, basically you will think about distributing them so the stresses will be controlled as well. Whenever you distribute a load on a bigger area, that means you're reducing the stress and eventually reducing the pressure on the slab. How is this kind of controlled or achieved by this setup? Is basically by changing the width of the stack. And as I said, that's where, if it was changed during construction, you would need to go and check it with the engineer again. It's not just you can assume it's working, because their original calculations was based on whatever spacing. So this P is here and that P is the other row, right? The width of the loaded areas, which it is represent the area of the posts, the cross-section area of the posts. If it's bigger, that means it's better. If it's less, that means you have more stress at that soil, the subgrade, which I showed you how the soil is actually having the angle of repose. When I was showing you, this was your slab, that's the soil. This is the post. There is a 45-degree angle of repose. If I have another green post, bigger, wider, your angle of repose will be what? Bigger as well. This is for the green. I'm just looking at a side view, and this is for the red. Okay, so whenever the width of your legs, the width of the supporting posts are bigger, it means it will reduce the stress on the soil. But if it goes skinnier, maybe you found a cheaper material, a better material, which looks skinny and it may look better, but remember, if it's smaller, it will cause more point load stress, and you have to double check if the soil gonna be happy to work with it. That's the last point you can see here. It is to do with the control joint. Last point we are talking about here. It is to do with the control joints, location of joints. We're talking here about the control joints, as we said, at the edge of the slab or the control joints, the slab will be stressed more. To clarify this, now, the angle of repose I was showing you, this is the slab, the concrete slab, there's a post, right? And there's an angle of repose, which will distribute the stresses over 45 degrees. Now, if we have an edge, let's say this is the edge of the slab here. The slab stops here, whether it's a control joint or it's the edge of the slab, just the end of the slab. What's going to happen if your post here? Your post is here. The angle of repose here, you're going to have it at 45 degrees, and here you have nothing. So effectively, what does it mean? The distributed area here is smaller than here. So that's really the reason. That's another reason why the forklift is very it's very critical to be at the edge beam of the control joint rather than the internal side of the slab. right? Yeah, so basically all these checks you would know, just to make sure that there won't be excessive flexure that will end up breaking the slab. We're talking about, these are the negatives, the negative bending. Whenever you change these properties I was talking about, you're going to be effectively changing this curve, and you may add the negative bending may be above the steel that was placed in the slab. And again, same thing, you know, the CBR and that question I showed you to do with the subgrade as well. So why we need to be careful in all those distributions and the load and the dimensions and the spacing is basically to make sure the concrete slab won't be overstressed in terms of tension and get cracked. And number two is the soil below it, the subgrade won't be overstressed as well, right? And we've already talked about the changing the storage layout. What does it mean in terms of changing stresses? All right, so construction. So all what we've gone through was the design concentration. You can see 60% of the information, yes, they will be calculated or estimated by the design engineers. But as a construction engineer, you need to know what do they mean and how to be applied for a project. Okay, if there is a specification, it does not mean it is only for the during service time. It can also be during construction, because you're going to be basically using the slab, and one of the things is you may be loading it more than what the user is going to be doing to it, because maybe it was just a lightweight shopping or retailer where you don't have vehicles on top of the slab, like Coles, for example. Most of the time they don't use forklifts. They're just going to be unloading and unpacking without vehicles. They just do it manually, just the trolleys. Okay, so that was the first part. Now, construction methods. I think we have, let me just give a start for 5 or so minutes, which one of the key things we're going to talk about here are, I will let you go through the joint types. The joint types, which I mentioned to you under design, but here we're going to see them. Now, in terms of joints, we said we have two main basic types. One is construction joint, which is you just need to stop the pour and start it next day, or there's movement joint where they're going to be there forever. Okay. Now, construction methods, I think we're just sharing with you pictures here. So it is, first of all, is we're going to have, as I showed you with the engineering documents for a project we're going to be using. So this is the engineering document. If you see the details here, it's asking to have to place on PVC vapor barrier. Yeah, lapped and taped. This means it is the black sheet. It will make sure the moisture from the soil won't come inside the property or the development. So this sheet is basically the one we're looking at here. You see this black sheet? Usually below the black sheet, you have the prepared subgrade. And yes, it needs to be checked as per the tables and specification we discussed. That's one thing. And then it needs to be compacted, the subgrade compacted to these limitations, which would have its own contractors to do. And you're going to be given a certificate that this is done. Then, yes, it's just a placement of steel. You're just going to be placing the steel and pouring the concrete. As I said, the steel can be the fiber steel, which is more expensive, or the steel can be steel bars. Okay. Now, this is just the vibration process. So this is just vibrating the concrete and vibrating the concrete. All this is going to be actually documented to you or given in those documents. If you read chapter number 2, which gives you what machine you should be using, the specifications and arrangements of the vibration, how long it needs to be done. But these kind of qualities are, again, implemented by the contractors who are going to be doing the work. Now, one thing interesting in this picture is this line here. You see this line? This is a control joint. I can see, we're going to talk about it more. You can see here, they want to stop the pour here. Okay, they want to stop the pour here. And they put those dowels. We call those dowels. We're going to talk about this a little bit more during the workshop. Just I don't need to rush because it's good to know carefully about the control joints. And you know the difference between control movement joints and construction joints. So this is basically a control joint, because definitely you would need a permanent joint here to open and close over the year. And these dowels, they're just going to allow, remember, these dowels are not the steel bars. We're not here. And I can't see it really. Maybe it looks like fiber steel is used in this mesh. You can see there's no mesh here. So fiber steel was basically used in this type of concrete slab, which will do the shrinkage, which will tell us that the ground here is really strong and there won't be heavy point loads that will require additional steel. The fiber steel was enough and all good. You can see here, this is a control joint, which we will talk about carefully later on. So they're just going to have, in a different day, they're going to do this side, right? And the slab would be able to open and close here. Just another picture showing you coming from a different angle. Yeah, you can have a look here. I still can't see any steel here, which explains to us this is, they didn't use the steel bars, they used the fiber steel because it was adequate to take shrinkage. But there is no steel. As I said to you, if the subgrade is very good and there is no point loads expected that will require the slab to flex a lot with a lot of tensile. And you remember that 5 MPa I was talking about was adequate, then you don't need to use steel bars. You can have just steel fiber in your concrete. This is just a cross section, which explains what this drawing was talking about to some stage. So these details we're talking about here, they are detailed, and this picture or this sketch is taken from that book. Okay, this is just was taken from book. The concrete slab, the industrial concrete slab is this one. See, this is the top, this is the concrete slab. In this case, or in this case, you can see it's got one layer of steel at the top, which was enough. This part here is that black sheet, yeah, to prevent moisture coming from the soil to the concrete. There is a sub base. Sub base, it is the topping we put, and we make sure it's well compacted, just in case the subgrade was rough. We can't have a rough because maybe some parts you got rock, sometimes you got a bit of sand, some places you got a bit of clay, and that will end up having uneven distribution of loads, which will compromise what we're trying to do. So what they do, they put a sub base before putting before the subgrade, compacted subgrade, they put a sub base, like a crushed rock or a sand, to confirm the whatever loads we have here going to be correctly distributed. Okay, and yeah, now and sometimes you're going to need some topping if used, just to make sure the slab is not impacted. Maybe if you've got some chemicals, you want to make sure don't get to the concrete, because some chemicals are not good with the concrete. So what I was, the angle of repose, when we have a post, this red is a post with a plate at the bottom, the base plate. You all now expert in. So this is the angle of repose. It's going to come with 45 degrees and go all the way to the subgrade. Yeah, this is typically 45 degrees. Yeah, and that was the angle of repose I was talking about always. Which we need to make sure whatever stresses we have here should be within acceptable limits. Right. So make sure you're familiar with with this section detail, and that's typically what you're going to see in 95% above of the projects. As I said, the pictures we shared with you here, it's obvious that there are no steel bars, and they did not use steel bars. So there is nothing, but what did they use? The type of steel I was showing you at the very start of the lecture, which is, what did we call it? Fiber steel. Where is it? We talked about it in our slides. Here we go. This type of, which I showed you. If you look at, I just show you from the internet, the steel fiber reinforcement. They are very small, 0.4 thick mil to 75 long fibers. All right, so I think really the rest of the notes will be about control joints, which I would talk to you about it during the workshop. So we're going to record that part as well for all the class. We're going to, during the workshop, when we meet, it's going to be face-to-face in Bendigo. I will finish about 20 or so slides, which, yeah, we're going to have a couple of pictures to explain things and what we mean with control joints. That's the key topic we have under construction. Demonstration, it is the joints. So I will talk to you about them next week. And then we're going to go through some questions for your assignment. Okay, that will be it for today's lecture. So we're going to continue from about here, Wednesday. And that will be it for today. Let me stop the recording. And if you have any questions, you can ask me. If not, we'll see you online or on campus in Bendigo